So here we have our second element, and for this element we're going to show that the if subcondition does not hold, and the way that we'll show this is by showing that the B part of the matrix is not full rank. And I already kind of started talking about this in the last video. What full rankness of a matrix means is that each one of its columns is linearly independent, which means is that if I multiply it by a vector, then this will give a unique output vector for any different choice of P, right? Because it will always be a different linear combination of linearly independent vectors. So in order to show that this element does not produce an inf substable solution pair, we have to show that this B matrix is not full rank, and the way that we'll show that is by showing that there exists a special pressure field, which will denote P with a square on top, such that B times that is going to be exactly the same as simply B times P. Yeah, so as a result, we cannot say that a multiplication of B with any vector will always produce a unique vector for any unique pressure, but rather we can add a certain oscillation to this pressure with according to this P with a square, and the result is still going to be the same. So again, this means it's not B is not full rank, which means that that does not hold. And that's going to be our strategy for showing that the if subcondition is not satisfied. Okay, so we'll proceed in pretty much the same way as we did in the previous video. We're going to construct a mesh of these element shapes, and we're going to play around with our expression for the B part of our weak statement, so the one on top here, and as a result also what's going to be in the matrix be in one of the blocks of our complete stiffness matrix. Okay, so our mesh is going to look, again, be a square, and it's going to look like this, where we have a bunch of square elements that tessellate our domain. So for this one, I'll have to introduce some more detailed numbering of my elements. The way that I'll do that is I'll start with K11, and then we have K12, K13, etc. And if we go up, we have K21, K22, K23, etc. So if we then take a closer look at this integral, well, the first step is still going to be the same. We're going to subdivide this in the result in each one of the elements. So we're going to sum over each one of the elements, going to integrate that element, and the sum of each one of these is going to be what would be the result of the bilinear form, the bilinear operation. Now, the same way as we did before, we can see that the pressure is going to be constant in each element, so I can pull that out of that integration sign. And secondly, now that I've introduced a more detailed notation here, I'll actually separate this into summation over i's and j's. So then we would get Kij of, well, I have only 1 degree of freedom per element for the pressure, so I'll also denote that one Pij. And sorry, that one would then again move out of the integration, so we have Pij times the integral over Kij of the divergence of V. So at this point I have an integral of a divergence. Well, that's exactly where the divergence theorem applies, and we can change this volumetric integral by a boundary integral. Yeah, so that's going to be the same thing as the sum over I, the sum over j of Pij. And now, after applying the divergence theorem, I would get an integral over the domain, or the boundary of the element Kij of v dot n. So let's zoom into one of these elements and try to work out the expression of this boundary integration. So I'll take one of these elements. We have element number ij, so we have a pressure ij in the center. And on each one of the corners we have 2 degrees of freedom, one for velocity in x, one for the velocity in y. The way that I'll denote those is in the lower left corner. I'll denote the ij, degrees of freedom, and then we count upwards. So we have a vector here that is vij in x and vij in y. And we have a vector right next to that one that is also an x and a y. And now it's going to be ij plus 1, ij plus 1. And at the top we have, I plus 1, j plus 1. Hope that's visible. And here we have vi plus 1, j. In x and in y. Okay. So that's now our degree of freedom numbering. So that's going to be the p and the v that we needed. How about these normals? Well, naturally the normals are the outward pointing ones. So we simply get 1, 0, 0, 1, and opposite ones of 0, minus 1, and minus 1, 0. So let's try to work out this expression. I have only 1 degree of freedom on each one of these edges for my relevant velocity. Or did I say 1? I mean, I have 2, meaning that this is a P1 expression for the velocity, a linear distribution. So v dot n, let's go over the top first. Or let me see. No, let's, yeah, okay, I guess it doesn't matter. Yeah, let's go over the top one first. So if I dot it with the normal, well, the normal has 0 on the x component and 1 on the y component. So if I dot a velocity with the normal on that edge, then the only one that I am left with is the y component of that velocity. Yeah, so at the top, I have an integration over this width, this size. So let's say, for now I'll just say that this is an integration of the edge, but we'll get back to that in a second, of only the y component of my velocity. Well, what's the y component of my velocity? Well, that's going to be the integral of this linear distribution from vy 1 plus, yeah, okay, so we have vy of I plus 1 j, and we have vy of I plus 1 j plus 1. And it's going to be a linear interpolation of these two. So if I somehow have an integration over an edge of a linear function, well, what's that? I can simply use the integration rule of a trapezoid, right? So I have a linear combination on two edges between two values, and then that's going to be equal to half of those two multiplied by the width of my domain. That gives me the integral over the complete expression. So half of two linear functions is simply going to be the sum of these two values divided by 2, and then integrated over the domain gives me simply multiplication with the edge size. In the edge size, I'll use the element width h. And so the integration of this expression on the top boundary gives me this. So let's try and work out the same integration on the right boundary. Well, on the right boundary, my normal vector is 1, 0, so it means that it only gives me the x component. Again, I have a linear interpolation from the x on the top node to the one on the bottom node, and from the trapezoidal rule, I can also say that the integration, this gives me the center value multiplied by the width, which is Vx I plus 1 j plus 1 plus Vx I j plus 1, those are the top and bottom values respectively, divided by 2 multiplied by h. So the same strategy gives me also expressions for the bottom and the left ones, where the only thing that I have to be a little bit careful about is the negative sign on the normal. So I get here 2 positive contributions and then 2 negative contributions. And those negative contributions are going to be Vij in x plus Vi plus 1 j also in x divided by 2 times h, and that's going to be, I believe, the one on the left part, right, because we're dealing with the x component. So it's going to be the left boundary, and the last one is going to be the bottom boundary, and that gives me Vij y plus Vij plus 1 y divided by 2 multiplied by h. Okay, so this simple integration over the element boundary of Vh dot n, I can explicitly write that out as the sum over of all these contributions. And that's an identity. I'm not making an approximation here. Other than naturally the approximation that's already in here from the finite element discretization. So again, if I now want to write out the total operation of this bilinear form, then I get b ph comma vh is the sum over I times the sum over j of pij times, and then we would have this lengthy expression that we just worked out here. Okay, so the way that we worked this out so far is we kind of took an element as the center of our picture, and then we produced the degrees of freedom that surround all the edges and the nodes of that element. Let's change perspective a little bit, and let's change perspective to a node-centered expression. So I'm going to look at a single node where I have a couple of elements. I will have, and the elements, well, they're also encoded by the pressure degree of freedom, right? Because I have only one pressure per element. So on the upper right, I'll have Pij, and on the lower left, I have Pi minus 1, J minus 1, and then Pi J minus 1, and Pi minus 1 J. Yeah, so that means that I'm taking this node here, right? So Pij is on the top right. So I'm taking this node, and that's also where I called my velocity simply ij. So this is going to be Vij in x and Vij in y. So rather than taking this sum to be a sum over all the elements, I can also take it as a sum over all the nodes. And that means that I'll have to sum all the different multiplications with the different pressures on each one of the elements. So I'll write this out first, and then I'll emphasize why that is the case. So this is going to be the same thing as the sum over I and the sum over j, where I'm now taking my node to be my center of focus. So I have h over 2, right? Because each one of these contributions was h divided by 2. Multiplied by Vijx multiplied by a couple of different pressures. And the same thing plus h over 2 velocity ij, but now in y, multiplied by a couple of different pressures. So the way that I'll center these pressures is I'll just go around the clock and look at each one of these element contributions and try to obtain the corresponding pressure there. So firstly, the upper right element, well, that's the one that we just worked out, right? So if I have Vijx, where do we have Vijx? Well, I have it here. That's the only one. So I'll have a Pij that I'm multiplying this with, right? So I have Pij simply. Okay, Vijx is multiplied by Pij. Same thing for, well, no, actually, minus Pij. That's kind of the point. So for Vijy, what do I have? Vijy, well, also a negative. So I have a minus Pij here. Starting to get a little worried. I have something else in my notes. Give me 1 second to try and figure out if I'm making a mistake now or if I made a mistake before. Negative y negative x. I think that's correct. Let's see what we end up with. Okay. So that's the one from the top right here. Let's change focus. Let's look at the one from the bottom right. So then our velocities would effectively be the ones here at the top left corner. So do we get positive or negative contributions of this pressure in this summation? Well, what are the ones that are corresponding to Vij I plus 1 j in x? Vi plus 1 j in x is right here. So that's also a negative sign. So in x I get negative p. So I'm getting a negative contribution of this pressure. And I have here I plus 1 j in y, I plus 1 j in y, so that's a positive one. Yeah? So I have here plus p I j minus 1. Okay, let's take a look at the element over here. From the element over here, this perspective, my velocities that I'm focusing on right now are the upper right velocities. So let's see, j plus 1, I plus 1, j plus 1 has a plus sign. So I'm going to have a plus of this pressure, p I minus 1, j minus 1. And in y, also I plus 1, j plus 1, I plus 1, j plus 1 also gives a positive contribution. I think I switched those, but the conclusion is the same. Now finally, from this element's perspective, we would consider the lower left node. So we have I j plus 1 and x, I j plus 1 and x, so that's a plus. So I have here a plus of p I minus 1 j. And lastly, v I j plus 1, that's this one. I have a negative value here. So I get a minus p I minus 1 j. Okay, So this is just a reordering of my degrees of freedom, but it's still going to be the same integral expression that we're actually computing here, right? So in the end, we're still computing B for any P and any V, but we're explicitly writing that in terms of the summation over different degrees of freedom. Yeah, so this is essentially the discrete system of equations that would be hidden in the B matrix. Now, why is that? Why am I going through all this trouble? Let me now define a specific pressure function. And the specific pressure function is going to look like this. So we're going to define this P with a square, right? So we're trying to find a special pressure such that the multiplication by B actually produces a zero value, right? So from this we can actually obtain that B times P with the square is equal to 0. That's the pressure that we're trying to find. If that pressure exists, then B is not full rank and we do not have this inf-sub condition. So I'll already spoil this for you. The pressure is going to look like this. Again, we have our domain, subdivision over different elements. And we're going to have a +1 value and a -1 value. And a +1 value and a -1 value. And I'll do this consecutively all the way across. And this is what we call a checkerboard pattern. Now we can think of the minuses as black squares and the pluses as white squares, and you get this checkerboard distribution of white and black squares of +1s and -1s in pressure. Yeah, so then B, P, well, by design of our matrix, that's going to be equal to B of this one. Yeah, so if we now substitute this distribution of pressures into these equations, then I hope that we get a 0, else I did something wrong. Let's see. So I'll focus on this node, right, because we're summing over all the different nodes now, over the i's and the j's. So that means that from this perspective, we have Pij, Pij minus 1, Pi minus 1, J minus 1, Pi minus 1, J as +1, -1, +1, -1. Let me focus on this first multiplication. I have good faith. I think I had a problem in my notes, not in the way that we're working this out right now. But I might still be disappointed. Let's see. So we have -1. So we have h over 2 times Vijx times -1 minus ij minus 1. So that gives me +1. Plus I minus 1, j minus 1. Well, that was +1. Plus Pi minus 1, j minus 1. Right, so this is a summation that gives me 0. So let's focus on the second sum. Well, I'm going to have plus h over 2 times Vijy of minus Pij, minus 1, plus Pij minus 1 is minus 1, plus Pi minus 1, j minus 1 is plus 1, minus Pi minus 1, j, I minus 1, j, minus. But definitely minus minus is plus. So that gives me also a 0. Yeah, so what this is showing is that if I work out all these sums over all these nodes, then irrespective of what my test function on V is going to be, right, irrespective of these degrees of freedom, this integral, which is the sum over I of the sum over J of these two expressions is always going to be 0. And since that integral was, well, essentially what we're computing with this matrix operation of BP, that is also saying that B times P with the square is equal to 0. And since there exists a pressure solution for which B times P is equal to 0, that means that B is not a full rank, and which means that the in sub condition does not hold. And what that effectively means from the perspective of actually computing something is that our computation, our numerical solver, finds infinitely many solutions, namely the solution that we would actually want to obtain, plus any arbitrary weighting of this zero energy mode. Right? So this is a zero energy mode. It's one of the ways that we call this. We also call this a spurious oscillation. Or a spurious pressure. Or a pressure oscillation, or a spurious pressure mode. Any combination of these words essentially describes the thing that we just illustrated, and you'll find these used throughout different literature in different ways. Yeah, and this is not really just a mathematical result. This is actually something that happens in practice. Now, of course, it happens in practice. It's kind of what we're trying to do here: show that mathematical analysis helps us understand what we're doing in numerical computations. So here we have the first example, and this is the one that we considered right now. Right? We have square elements P1 or Q1 for the velocities, Q0 for the pressures. We actually get a very decent looking solution field for the velocities, and actually a very good one, and we'll get back to that in one of the future videos. But the one that we're interested in right now is the solution for the pressure, because that's where the in sub condition was important. And we actually find that this is precisely showing what we just pointed out. We get this true solution of our pressure, the one that we want to obtain, but it is overlaid with this funny looking up and down jump. Yeah, so it's going up and down, up and down, up and down. That's precisely that checkerboard pattern that is overlaid on top of the true pressure solution. And I guess the fact that we do obtain a solution, I'm not entirely sure why that is. I suspect that it is due to numerical roundoff that the solver is still able to find a solution. But this is also showing that this spoiling with this checkerboard pattern could have been in any magnitude. You can get very large jumps from one to another, from one element to another, or small jumps. You might not be able to recognize the original solution at all. Right now we do sort of recognize the original solution. But again, it's just an unreliable pair of elements, and we can't really rely on being able to use these for a certain computation and get good results, right? We might not be able to recognize our true pressure field due to the way that this is spoiled. Now, again, just like in a previous example, we saw that this result is highly dependent on our computational geometry. I assumed a simple square, and our mesh, I assumed a uniform distribution. But also for different geometries and different element distributions, you would get other pressure modes that might not be as straightforward to show and to compute, but they would be there, and they would also spoil the result. Right? So these are now two different elements that we're able to show just by counter examples that we're not going to get good computational results. Okay, and in the next video I'll then actually move towards an element that does work, and then we'll try to find strategies for being able to predict whether an element will not work or will work or not. Right? So it's going to be tricky if you're not. You probably don't want to perform this analysis for every new choice of element, so you want to get a better feel of whether an element's going to work or not with more straightforward tricks than what we did in the current video. Okay, thank you for your attention and see you in the next video.